everyone, so this is kind of our video going over Newton's three laws. We'll look at them maybe again kind of for round 2 through a different lens, but that'll be much later in our year together. So really this whole unit is about this thing called dynamics. Dynamics really is just the study of motion and the forces that cause motion. So really dynamics is more or less broken down into forces, while kinematics, our last unit, is on motion itself. Now, with that in mind, the unit of force is called newtons, which has the symbol capital N, not newtons as in a fig Newton, not a Newton as in Sir Isaac Newton, but a Newton where 1 Newton is a kilogram times a meter per second squared, or meter per second. And it's almost kind of like this is a mass times an acceleration. So it's kind of like force equals mass times acceleration, something kind of like that. Now, even more kind of to bring it into the real world, a Newton is actually the force or the equivalent force of gravity pulling down on this apple. And so this is actually literally a 1 Newton apple kind of hanging here. Or kind of looking more specifically, we have these in our class. It is a force sensor. It actually can measure mass on this side. We have grams right there. We have newtons right here. So if I go and I hook up my apple directly to it, and I just let it kind of stabilize there, we can then kind of zoom in and see, hey, it is actually at 1 Newton on the Newton side, which is about the same thing as 100 grams on the mass side. So really, Newton is our unit for force, okay? So when it comes down to it, we have 3 laws of Newton's. It's convenient if you know the order and you can go, oh, it's the first or the second, but really the thing that matters is that you understand them. So the first law of motion is that an object at rest, something at rest, kind of stays that way, or an object in motion will stay that way unless it's acted upon a net force. And net is kind of the important part there. Net force is really like an overall force. So in the terms of my apple hanging from my force sensor, my apple is not doing anything. It's staying there. Even though there's a force pulling down on it, that's gravity, there's a force pulling up on it, that's the tension in here. And so there's no net force on it. If I were to start pulling up on the thing, it would accelerate up, because while I'm pulling, there then is a net force. It's kind of an overall force. So really this kind of is why if you look around your house or your room or wherever you are right now, nothing is really in motion, or most things aren't in motion, because most things don't have a net force, even though there are forces acting on everything, whether it's just gravity pulling down on you in your chair right now. So, and it's the same for things in motion. Something actually stays in motion unless a net force acts on it. And a net force can change the direction of it, a net force could slow it down, or a net force could make it go faster and faster. So kind of in regards now to these net forces and kind of what they can do in making things go faster or slower, our second law here says that that same kind of net force, this kind of overall force, will cause things to accelerate. So we have a net force causes acceleration, and the thing that really relates force, net force, and acceleration is mass. If we kind of forget the mass part, they're just proportional. But when we throw mass in, they end up being equal, and then we kind of get this equation where, again, these little arrows on top just mean that force is a vector. So it has not just a size, but a direction, and acceleration is the same thing. Most of the time, we won't use the little arrows, little hats on top, because it's not included on the AP tests, really. So even though this might be the version that you are more familiar with, this is unfortunately the form that's on the AP equation sheet. So it's just the way that it is. I don't get to make the rule on that. But really, this form is the form that will be most useful for us often. But really, this is the form that you have to be familiar, or at least aware, is just kind of the version of it on your equation sheet, okay? So again, a net force is like that overall force. Okay, and it's the net force that causes something to accelerate. The bigger the net force, the bigger the acceleration will be, as long as the mass kind of stays the same. So kind of to break things down, just to give kind of 2 little analogies here. If, let's say, I had, I don't know, $15, right? I made $15 today. Solid. That's pretty pathetic, but cool. I make $15. I owe you 10. So there's 1, there's 2 gone. So the net income that I have made is only $5. I actually did have 15 that came in, but 10 went out, so my net amount is 5. It's kind of that overall I really only made 5, even though for a while I was holding on to 15, okay? So that's kind of a simple analogy for it. And then here's kind of a real world kind of physicsy analogy. Let's say I have a block and it has a mass of 1 kilogram, and there's a force pulling to the right, and usually we say that to the right is the positive direction, and it has this kind of magnitude of 10 newtons, and there's a force going in the opposite direction, this force 2, and it has a magnitude of 7 newtons. So really, the way that we would write out that net force is kind of 2 ways. The first way is, well, we just write out this kind of symbolic equation showing that the net force is really, since these are going in opposite directions, the difference between these 2 forces. And typically, and most of the time, we're assuming that the positive direction is to the right and is up. That's just kind of how it's taught in kind of our math classes when we learn things kind of growing up. And so that's why I said that this force is my positive one, and force 2 is kind of going in my negative direction here. So we can then kind of go in, plug in the numbers for it, 10 minus 7, that gives us 3. And since forces are a vector, they have a direction, it's to the right, all right? So kind of a neat thing here. We're not just plugging into this F equals ma, we're actually kind of writing out a different way of looking at this net force itself. How do we write that thing? Well, we write it as the combination of whatever forces are physically present in the scenario, okay? Now, we could take it a step farther. If we know the block has a mass of 1 kilogram, and we know now the net force, we could go, hey, well, we know F net, we know A, let's go ahead and find, or we know F net and we know M, let's find the acceleration. So we can plug directly into the version on our AP equation sheet, and we can get that this has a acceleration of 3 meters per second squared, or 3 meters per second per second. And it really comes down to the fact that a Newton actually, I don't think I mentioned it here, or we did mention it, is this. So we just kind of can substitute that in and see that, hey, well, there's a kilogram secretly up top in the Newton here, and there's a kilogram down here, so the kilograms kind of cancel each other out. So the third law, you've probably heard it in the format of for every action, there's an equal and opposite reaction, but it's really kind of for every force, there's an equal and opposing force. And so, for instance, let's just kind of look at you right now, whether you're standing or sitting or laying, you're not accelerating, you're not crushing through the earth going faster and faster, and you're not levitating up into the stratosphere, right? And so that means that there must be 2 forces that are equal but opposite to each other. So they're the same size, but they're opposite directions. So for us, or maybe it's a block kind of like this, well, we have the force of gravity that does in fact go down. And the force of gravity is just the mass of something times g, where g is that 9.8 that we keep using. It's the acceleration due to gravity. So that's our way to find kind of the force of gravity. And the neat thing is when you go to the doctors or whatever, you kind of step on the scale and get weighed, right? Really, all they're telling you when they take your weight is that is the force of gravity on you. If you went to the moon and you stood on a scale and got your weight, well, G is smaller on the moon. It's not the Earth's gravity anymore. It's the moon's gravity now. And so you'd end up having a smaller weight, even though your mass is the same. The amount of atoms and things making you up is the same. Your mass is the same, but you'd have a smaller weight because that force of gravity on you would in fact be less, which is kind of neat. But now kind of coming back to this, well, the force of gravity is going down, and whatever you're sitting or standing or laying on is actually kind of pushing back up and kind of resisting it. And so this Fn, with a capital N, is called the normal force. And normally it is present unless you're in free fall or you're in space or something. And it's this force that opposes gravity on surfaces. The normal force actually is responsible for friction as well, and we'll look at that later, but that's kind of getting a little bit ahead. And so again, writing out the symbolic net force here. The net force is the leftover force, the remaining force. And so the way that we would write this, well, would be Fn minus Fg, because Fn is kind of going in that up positive direction, right? And Fg is going down in that negative. So combining those two would look like this, okay? If you said that up is negative and down is positive, besides being weird, you would just kind of flip the order of these two. They would just switch spots, and then you would get kind of the same thing in the end. Now, the neat thing is that since Newton's second law says that not only is the F net, this part on the left, kind of like this symbolic thing we're trying to write, but it's also equal to the mass times the acceleration. And so in the case of this, well, we have this guy that's kind of from writing or looking at the physical scenario, we kind of figured out this symbolic way to represent the net force. But then we can also say it's equal to the mass times the acceleration. But since me sitting here in my chair, or you standing or laying or sitting, or this block on the countertop isn't moving, that means that the acceleration is 0. So this whole term is in fact 0, which is kind of neat. So this is really F net equals ma, but this middle part is our way of representing the net force in this situation, actually. All right. And so if this right side is 0, well, I can just add Fg over to the right side here. And so it kind of makes sense that the normal force is equal to the force of gravity. So those two are, in fact, equal but opposite. And that's why this box or block or you or me isn't crushing through the earth again and going faster and faster, and we're not speeding off into the atmosphere, okay? And so in the end, if we need to find that force of gravity, you would need just the mass, and you would just multiply the mass by g. And if you were on the moon, you'd just have g for the moon instead of 9.8. And so kind of to summarize, it's really only net forces that cause acceleration. But because most things around us aren't moving in the world, at least kind of just looking around the room, a lot of objects are stationary because they don't have a net force. They have forces, but not a net force. That's it.